Hello again. So far, we introduced Friedmann equation, which is the basic equation of relativistic cosmology. Its solutions describe how is the universe expanding as a function of time, and therefore how a distance between any two different objects can be computed. So here is Friedmann's equation in its newly expressed form as a function of cosmological parameters. It's a differential equation. However, in order to solve it, we need something else. The expansion of the universe at any given moment is determined by the mean density of matter and energy in it. As the universe expands, that density changes in different way for different components. The equation that specifies how that is changing is called the equation of state, and it is often expressed as a relation between pressure and density. In its simplest form, it is just a multiplicative constant, usually denoted as little w. So the equation of state parameter itself is sometimes called the equation of state, and note that this is a fairly arbitrary functional form. In principle, equation of state could be much more complicated. However, this is the simplest one, and so it's a good starting assumption unless it's proven that something else happens. Also, we know that some of the major components, like ordinary matter, energy density, or cosmological constant, are behaving in this fashion. So there are some special values. W of 0 means that pressure is 0, and so that's a non-relativistic matter, just galaxies or atoms that do not interact other than gravitationally. W of 1/3 corresponds to radiation, photons, or relativistic particles of some kind. And W of -1 corresponds to a constant energy density that doesn't change even though the universe does expand, and that is suitable for cosmological constant. So let us consider these three simple cases: matter, radiation, and cosmological constant. In reality, the universe has all three of those, plus maybe other things, and there is a mixture, so all three have to be included in Friedmann's equation. So each of those will evolve in a different fashion, because each one of them implies a different behavior of density as the universe expands. And so as the universe expands, its density changes, that affects the expansion, and so on. All right, so how does the density of the matter and energy change as the universe expands? Let's start with the three simple cases that we just introduced earlier: ordinary matter, radiation or relativistic matter, and a cosmological constant. I'll just number them 1, 2, 3 for convenience. So if we put those in the fluid equation, which is essentially continuity equation, and hopefully you have encountered it when you're learning about fluid dynamics, but if not, go refresh that knowledge. So let's substitute three expressions we've seen before in the fluid equation. In the first case, behavior of ordinary matter, the equation becomes what's shown here, and as you solve it for the density as a function of expansion factor A, the solution is familiar, that density goes as inverse cube of the size. In the second case, for the radiation or relativistic particles, things are a little different. Just like with the real matter, the density of, say, photons, numerical density of photons, will change as inverse cube of the size. But in addition to that, the energy will also go down by 1 power of density because of the cosmic expansion, the wavelength stretch, and therefore energy goes down. So in that case, the density goes as inverse 4th power of size. And finally, in the third case, the derivative is 0, and therefore the density must be constant. So in general, we can express behavior of density as an expansion factor R, or A, on power of -3 times W plus 1. And let's see how that works with the three cases we've seen. If we substitute values that we defined before, 0 for the regular matter, we do get the density goes as scale factor minus third power. If we assume that it's 1/3, then indeed we recover dependence of radiation energy density as scale factor to the minus fourth power. And finally, if it's -1, then density stays constant. You may remember that energy is not conserved in an expanding universe. Well, here is an obvious case. The universe has a constant energy density in terms of, say, ergs per cubic centimeter, but there are more cubic centimeters as it expands. So there is more and more energy in the universe. An interesting case is if W is less than -1. In that case, the more the universe expands, the more energy it gets, and the expansion keeps accelerating even more. And in fact, this leads to what's called a big rip, where the universe expands so dramatically that atoms will be torn apart as well as everything else. But rest easy. Very likely we do not live in such a universe. And even if we did, it will take many billions of years. In a realistic universe, there'll be a mixture of these components, and the expansion will change. At different times, different components will determine how the universe is expanding, because some of them decline in density faster than the others. Also, remember that we have assumed that W is constant, but it need not be. In itself, it can be changing as a function of time, but we have no theory whatsoever which could indicate why would that be and how. So this is how we solve Friedmann equation. The output of it is really how the density of the universe changes as a function of time. Next time, we'll consider some examples of actual cosmological models.